were you last night?
Had other stuff to do, and we work very slowly.
Actually, we worked pretty fast this time. Because I was there.
You didn't actually do it?
Yeah. We did 24.
I worked out the whole double play tournament thing.
Good.
You done that?
Yeah,
we did.
Just put it in there and I'll
Collaborative effort.
I'll go in there. That'd be good. Thank you for doing
You know
that.
who helped me in mine? The crackhead patient that was last night. Seriously? Yeah. She? Yeah. Oh, I just disgusting.
Oh, since when did you have 4 people in your thing?
Help me with my homework.
I did.
Your starting thing?
And actually, she didn't really help that much. She said,
Started
I don't know nothing about all that. You
No, I
want to
started
be a
my
smart girl.
Let me try that
I
again.
said,
I
did not get it.
What is the review for
Exactly.
exam?
Not particularly.
Is this what your answer was? No. It doesn't have acceleration.
What's your deal by inflation?
Yeah.
I should have put G.
Yeah, this is G.
What was that?
But yeah.
I don't think the answer is the same as mine.
It's similar.
No, similar to
If I
something.
simplified it.
Did you finish that?
Not even close. I like walked out and was like, all right, that's gonna be my gimmick test.
That which gives me the most fried chicken, which is my friend. I love
Do better. Work faster. Yeah, I think I just have to work
What we use.
over and over again.
Yeah, we.
Yeah.
I don't feel like I'm slow.
Yeah, pretty much, yeah. What's that?
Wait, chapter 5 was on the
The
test?
thing that was on mine.
No.
But we
How
worked
is
through.
this on chapter 1?
Because there's another one where we skipped like the one that had a friction in it.
Ew.
We skipped like the last 2.
Oh, look, I see.
As
I forgot that happened. So we already did a lot of
No, Stewart said that.
Actually,
Now you get your people right. I said Boston. He said it's scary.
figure out what he's asking.
And somebody else said something.
At the beginning of the equation,
The
then it makes you
Howling
realize
test.
where you're going.
Are we allowed to come in
Are we allowed to talk about
This is
stuff?
actually a
Will I get extra credit?
I can dress up as Kenny's physicist or something?
Yeah.
For lunch time?
I dressed up as like
Next Thursday.
gravity.
It's like comedy class.
This will be something to
Next Thursday.
know where you're going.
Yeah.
I'm gonna dress up as Earth Centripetal Force.
I'm not sure I did.
What if I dress up as Robin?
But, oh.
As what?
Okay, let's see. We have slight change in assignments. So for Friday, you'll have to do a practice. That is, it's a review for the exam. So the exam is going to be Halloween. Yeah. All Souls Eve. 7 to 8 p.m. in Kinard room 101, which is a big auditorium on the first floor. It will be proctored by the grad student you met previously. So for Friday, I just passed out, and there's also available on Blackboard a review. It's like a practice exam, so I want you to do it thoroughly. Now, I'm not constraining myself to put onto the exam exactly what I'm giving you out for practice, right? Or even generally, except by way of principles. That is, you should be able to understand how to apply these principles, and I may give you some specific examples in the practice, but you've got to be able to apply the same principles to more other situations, right? Okay, so do the review then for Friday, and we'll go over it in class. That's what we'll spend Friday in class, just doing the review. All of the we'll review all of the questions that are on that sheet that I just handed out. It's also on Blackboard. Yes, sir, Mr. Trimble.
I know you weren't for the first time, but are you going to be there for the exam session?
No.
That would be cheating. I would just look at Daw's mind and I'll just figure out the answers.
Yeah, just read my eyes.
Because I was going to ask you to dress up.
Oh. So I could ask my graduate student to dress up like me.
Oh, please.
That'll put him on the spot. He won't know how to do that.
somewhere online, is there a schedule of the after class exams?
Yes, ma'am. It's on the registrar's website. They're called common exam times. So they're common exams for chemistry, physics, and some math classes, I think. And so on there you can go see the dates. They're set out at the beginning of the term. You can see them all. I think this may be the last one for us. I'm not sure that there's
Okay. I have my
there
own.
might, is there, wait a minute, I can answer that question.
Does that include the final? Like,
No,
do we
I'm
have a
sorry.
scheduled time for our final?
Yes, there's a scheduled time for the final. There's two times for the final. Just a minute. One question at a time. We're still on her question. November 21st is the next one, and that is the last one.
Hey, I'm not working that day.
Okay. Your question. What was it?
When was our final exam?
It's again, go to the same place, but there's a choice for 2 times for us. There's the time for this. There's the time for this period. So there's a time slot for that. Then there's also a time for the common exam, which is different because the common exam doesn't apply to any specific period, right? It applies to all of Physics 122, for example. All of those will have a common exam time. So we have 2 time slots during that week.
Which one are we using?
Right. And so in the past, I have left it up to the class somewhat to discuss this among themselves. The last couple of times, there has been no agreement on this. So in that case, I picked the latter time. Unless there, let me put it this way. We'll take whatever time is later, unless there is unanimous agreement in the class that we'll move it sooner. And by unanimous means I get one anonymous email saying I don't want to do that earlier exam and I don't want to tell anybody about it because it'll put pressure on me or something. We'll do the later time, okay? We just opt for the later time. Even if it's the last day of the term, you know, everybody else wants to just go home. Okay. All right. So for Monday, so this is considered part of Chapter 5, homework number 5, I think. Is today's number 4? So for Monday, we start Chapter 6, number 1. In the schedule that I passed out earlier, you were going to start Chapter 6 already for Friday. So I'm moving that a little bit later, inserting a review day for Friday. The review will cover what's basically the principles that are on that review sheet for you, but all of chapters 1 through 5, right? I mean, that's what we're doing. Okay, let's see, before we get started on the homework, I want to discuss the idea of a term. I'm wondering if this term is familiar to you. Scientism. So scientism, let me define it here specifically in relation to what we've done here in this class. Scientism would be an assertion that the empiriometric is the only certain or scientific mode of reasoning. That would be a scientistic statement, that the empiriometric is the only really valid, certain scientific way of reasoning. In other words, measure it and put it into an equation. According to the empiriometric, you really understand something when you have a mathematical theory. That's when you really, that's the goal in the empiriometric, is to accomplish that. Okay. So, now this is not even self-consistent. Right? But before I get to that, it's not even self-consistent, but let me explain exactly what I mean. So we have physics is what? What is physics? Rigorous study of changeable being. From Chapter 1. The empiriometric is a part of that. And it's a very important part, because as we have been seeing now, when we're moving through these chapters, we've got these mathematical procedures by which we can solve problems in terms of what is the velocity of something when it reaches the bottom of the waterfall or that kind of stuff. Okay? So this is the empiriometric. scientism would be to say, let's imagine that somehow we could just pull the empiriometric out of all the other stuff. All the explanation, all the understanding, all of the principles that we developed in the first chapter. The scientific would be to say, somehow we can pull this out and just use the empiriometric by itself. That would be the scientism, the scientific point of view. Now notice, in the first place, scientism is not even self-consistent, because that statement can't even be proven in the empiriometric scheme. There's no equation that you can use that would prove that this should be the way we would go, right? There's no means by which I can justify that statement on its own grounds. I can't measure it. I can't write an equation that relates it, right? It involves concepts that are beyond the empiriometric. So the empiriometric itself would say, if I can't measure it, it's meaningless. Don't even talk about it. But that already calls into question even the method itself, even a statement like this. Okay, so the scientism has a lot of effects. It's very prevalent. You find it, I think, among a lot of scientists, at least this assertion. It's not even a self-consistent statement, right? Because you can't really make this assertion without having some kind of other argument to assert it that falls outside of this. So it's not even a self-consistent statement. So it's a confused statement, and you find many people asserting it, but they can't really do it in a self-consistent, justified way. But it's very prevalent. And you find, in fact, that what this does, one of the effects, this has many effects on science, and one of them is that it destroys the simple meanings of words.
What does it say?
Destroys the simple meanings of words. Like a person. I can't measure a person. I have no way of putting that, relating that in any sort of mathematical process. So if I assert personhood, what a person is, that's something that's outside of the empiriometric. It's not something, it's something that could be understood within physics, generally speaking. The study of changeable being, a person is a changeable being, but it's not something that is something that can be accessed through the empiriometric in a full way. We lose the essence of the thing. So it destroys the simple meanings of words, because you can speak to many people who are wrapped up in this empiriometric way of thinking, and I don't know what a person is anymore, right? I've had that conversation with many people. One student said, well, I know that this is made of atoms, and I know that I'm made of atoms, and if I rub my hand on here, then my atoms are left on it, and some of its atoms are left on me. So I don't know what a chair is anymore. I don't know what a person is anymore. As though somehow in this empiriometric way of thinking, you have forgotten everything before, which, again, can't be done. You don't forget what you knew before. You don't forget that you're a person. But he's somehow thinking he has to pretend that he doesn't know what a person is anymore. And so it destroys the simple meanings of words as we understand them in their simple terms. Cause and effect is another thing which is destroyed, because there is no measurement that can tell you this causes that. It's not a measured thing. Truth. If, in fact, science is about truth, this would be something that the empiriometric person, the scientistic person, would say no. The scientistic person would say no, so not according to scientism. Certainly it is about truth, but the scientistic person would say no, it's not about truth. We've got some measurements and some equations, and we can make it work, but there's no truth to be found. So what goes along with this then is a kind of corrosive skepticism and a lack of ability to spell. A kind of corrosive skepticism because you're even questioning what is the simple meaning of words that person, anything like that. I mean, if you seriously think that you could question what a person is, I mean, in a kind of sophistic way, that isn't just, I don't know what a person is anymore. If you really do come to that point of mind, you're really a corrosively skeptical person. In fact, that nobody can really say anything to you without you just saying, well, what the heck does that mean? So it has a very deleterious effect. And so what Rizzi is doing here with this is to restore the proper relationship of this method called the empiriometric to the fuller understanding of science. Because this physics as the study of changeable being really is, and science understood as the search for truth, really is why I think most of you got into it. Because you're curious, you were interested, you wanted to know why it does that. And reducing it down to simply the empiriometric, measure it and write the equation and solve it. Shut up and calculate kind of attitude, I think, just destroys science, frankly. And it certainly takes a lot of fun out of it for a lot of people, except that it's that part. You know, if you're good at cranking, good at that part, that's the part I like. You know, that's some people just want to focus on that. But it destroys the proper relationship of science to the person. Okay, so now let's go on and start doing some empiriometric stuff. Having said that. So let's take, so the first example, I think, if I remember correctly, I've only got the solution here. Is this a block sliding down a ramp? Oh, I'm sorry. It's this machine, isn't it? It's got a pulley like this with a block here. Is this right now? Okay, good. Thank you. Okay, block B is hanging on the rope, and block A is sliding on the surface, and there's friction here. And so now we want to know how fast is it moving after this block has slid a distance x, after that block has dropped a distance x, which means that the other block has slid the same distance x over the surface. So how fast is it moving? Okay, how do we begin something like this? Well, this chapter being on energy and the work-energy theorem, it seems likely that we want to go back to the work-energy theorem. So let's go back a minute. The work-energy theorem is this, that the work done by the forces that are present is equal to the change in kinetic energy of the system. So now this kinetic energy can be the combined kinetic energy of the two masses, so that's fine. The work involved here, well, we have different forces that are involved. So now let's go and consider the forces. So a force diagram is in order. So we have sandpaper here. So what are the forces acting on this body? Now it's sliding. So we have to take, and it's sliding in this direction. So that's the direction of sliding. So what are the forces acting on this body? Tension. Force of what kind of friction? Kinetic friction, which is nice because it's easier to deal with than static friction. Static friction is a little bit more complicated. All right, what else? The weight of the object due to gravity, and then the table is pushing back up on it to keep it from moving. So, but only two forces do any work. Which two forces do work? Friction and the tension, right? They both do work. The normal force does no work. Why is that, Mr. Creer? Why does the normal force do no work as this block slides?
There's no change in the y direction.
Correct. There's no displacement in the direction of the force. And the same applies for gravity. Okay, and this other body. Mr. Disharoon, what are the forces involved in on this body?
Just mg and
okay, and this is...
Or tension, sorry.
Yes, yes, thank you. MA, so this is MBG and tension. Same tension because why? Yeah, the pulley is massless. So when we get to rotating, we'll come back to a problem like this where we have a pulley has mass, and we'll have to take into account the mass of the pulley. It's rotating, and so it will have kinetic energy as well. At the present, we're neglecting that. That means that these two masses have to be much more massive than the pulley. If we can do that, then the effect of the pulley is negligible. Okay, so now the tension and gravity both do work. Let's see. Let's look at body A. So Ms. Shaven, how about the sign of the work done by the tension? Is it positive or negative?
Positive.
Right. And how about friction?
Negative.
Negative, it's the opposite. And so Mr. Fanning, how about on the other body, body B? It's moving down. So how about the work done by gravity?
It's positive.
Yes, and tension.
It's negative.
Notice that tension does positive work in one place and negative work in the other place. And in fact, does the total amount of work done by the rope, do they cancel? Right, it does exactly the same amount of work. Okay, so in other words, if this top block moves a distance x and the bottom block moves a distance x, the tension does Tx in one case and negative Tx in the other case. And so you don't even have to know what the tension is in this problem to use the work-energy theorem, because in this particular case, the work done by tension on the entire system is 0.
You heard that?
Isn't that convenient? Okay. All right, now we have two different things here. We have the work done on body A is then T minus Fk x, and the work on body B is going to be Mbg minus Tx. And so the total work done on the two, that is the work done on the system, is going to be then Mbg minus Fkx. Okay. Now in this work, let's just go ahead and finish this then. The change in kinetic energy, if the body starts at rest, Ms. Ma, if the body starts at rest, then what is the initial kinetic energy?
0.
Yeah, the system starts at rest. And so this is equal to the final kinetic energy. The initial is 0. And if both masses move at the same speed, do they move at the same speed? Ms. Ma, do they move at the same speed?
Okay, I'm struggling with this. If they're moving at the... Wait, can you repeat the first part of that?
Are these two masses moving at the same speed?
Yes.
Mm-hmm. One's moving to the right, one's moving down. They're
But
moving in different
because
directions.
they're connected by the fixed length of the rope and the tension is the same.
Excellent. So the kinetic energy after they start moving is a sum of two terms which then have the same speed. So we can just add it together, add the two masses together. So the kinetic energy is 1/2 the sum of the masses times the square of the speed. Okay, now by the work-energy theorem, we can therefore say we can find that relationship in the velocity by Mbg minus Fkx. And we're almost there. What we don't have here is Fk. What is Fk?
U and 1J.
Okay, so it's mu k in, generally speaking, but you've also made the additional step, I think, Mr. Averett, that this is the normal force is equal to the weight because it's in equilibrium in the vertical direction. There's no acceleration in the vertical direction. So n is equal to mag. Okay, and so that gets us then the expression that we have v is equal to the square root that I have here in the solution. G drops out. I'm sorry, G is common factor, so we pull it out. That's the velocity then. So let's examine this a little bit. Dimensional analysis. Let's do a little bit of dimensional analysis on it. So the velocity we want to have be length per time. So let's look at this whole thing. What is the dimensionality of G?
Length per time squared.
And Mr. Jackson, the dimensionality of X?
Is length.
Okay, and how about all this stuff here? We have the ratio of masses over masses. What about the mu k? What is the dimensionality of mu k, Mr. Jackson?
Mu k is a force, so it would be 1.
It's dimensionless.
Dimensionless.
Yes, so it is 1. So if we refer back here to this equation where we use mu k, F and N, Fk, the kinetic force of kinetic friction, and N are both forces, so mu k is dimensionless. So this expression is just simply mass over mass, and that ratio is dimensionless. So we have that inside of the square root here, and so this in fact does have dimensions of length per time. Good.
You made it seem so Like, you don't understand how much trouble we were having with this.
Oh, I think I
Actually,
got it.
I went to the computers and tried to get them to explain it to me. And it's still.
I actually found the force of tension.
Okay, but so we're going to examine this problem a little bit more. There's a lot of interesting stuff in this problem. The work-energy theorem makes it easy because you can avoid having to do certain things. But if you want a full analysis of this problem, you can actually solve it the old way. So I'm going to do that here in just a minute. But I want to point out a couple of things here. Let's go back up to this. Notice that in the work that we calculated here, is this work due to a conservative force or work due to a non-conservative force, or is it got some of both?
Some of both.
Now, gravity is what?
Conservative.
Friction is definitely dissipated. The work done by dissipative forces is always negative, and you can see the Fk there, it comes in with a negative, and Fk is mu k mg negative. So that term, that work, is negative there. It might be a flag. That might be a dissipative force. That's not the proof. Remember what the distinction is. For a conservative force, the work doesn't depend on the path. For a non-conservative force, it does depend on the path. Okay, so we could have separated this problem. We could have done it differently. Remember that W can be separated, the work done can be separated into, I'll stop. The work done can be separated into work by conservative forces and work done by non-conservative forces. We can separate the forces according to their type. And the work done by conservative forces is the negative change in the potential energy associated with a conservative force. But we can't write a potential energy for friction because it's not conservative. There's no potential energy that you can write for a non-conservative force. Okay, so the negative of the change in potential energy. So what's the change in the potential energy? Well, yeah, it's the top block. Does it change potential energy? No. The bottom block does. Does it increase or decrease its potential energy?
Decrease.
Yeah, decreases. So delta V is minus mb gx. It loses potential energy, right? So, and so you can see this this negative V here. So if I write a negative V here, there we go, mgbx. That first term in the work that we had up here, mbgx, is also the change in potential energy. We could identify this piece as being the change related, this with the x, as being the negative of the change in potential energy. So I could have done this problem a little bit differently, which is to say at the beginning I simply write delta E, which is delta K plus V, is equal to the work done by non-conservative forces, work done by friction. So I could do it this way as well.
Okay, that makes sense.
So if I turned off the friction, then the total energy would be conserved. But there's friction present, so I have to take into account the work done by friction. And so the loss of total energy is shows up as work done by friction. Okay, so and I can go back and look at this expression for V here. For V, here's the mu k. Suppose I turn that off. That would be in effect turning off the work done by friction. And so now I've just got a potential energy, kinetic energy argument. I'm just trading off kinetic energy for potential energy, or the other way around, potential energy for kinetic energy in this case. So what starts off as potential energy, which is the block is up here, chapter 5, and goes down here, MB, shows up as kinetic energy for both blocks because of the rope. Okay, now that's the simple way, and it's the way that the point of chapter 5 is to demonstrate that. But there's another way, which I could have gone back to what we did in chapter 4. All right, that's fine, no problem there. Just takes longer. You can do it. You should get the same answer. It's just going to take longer. The work-energy theorem saves you from having to do it, but it doesn't get an answer that it saves you from having to do some of the work. But it doesn't change the answer. Okay, so we go back again. Let's define a coordinate system. X for A, and let's see, YB. And we could write down the equations of motion. Ma xa double dot is equal to T minus mu k minus Fk, which is UK mag. And then we could also write MAYB double dot is T minus MBG. And then we need to put in the constraint of the rope. So how do XA and YB, how do these accelerations relate to each other? Notice that I've defined my Y as coming up from the floor.
Opposite.
Yeah, so they're going to be opposite. The accelerations will be opposite because of the way I've defined it. Okay, and now it's just an algebra problem. You want to solve for what? Okay, Mr. Vestal, what would we solve for here?
Tension?
Yes?
Oh, and x double dot.
Right. The accelerations of the two masses, all right, is a acceleration of A and acceleration of B. We solve for those three things. In terms of, we'll have in the answer, we'll have the masses G and mu k. Okay? So I could solve for the tension in this problem. I guess Mr. Flanagan knows the answer to that. All right? And so now we can solve this problem, and we have now what kind of motion is this? Mr. Tremblay, what kind of motion do we have for these bodies? Well, we've only studied
uniform linear acceleration.
Exactly. Uniform linear acceleration. It's not uniform translation because that force is acting on these bodies. They're accelerating, and the forces don't change, so the accelerate, and the mass doesn't change, so it's uniform acceleration. So we could solve for the velocity, right? The velocity of A is going to be its initial velocity plus the acceleration of that body times time, right? And the velocity of B would be the acceleration of B times time, and the distance of the distance will be then XA, because it starts from rest, the distance it travels is this. Let's see. So I'm going to have to say here, this is going to be negative, right? It's going to move in the opposite direction. YB here. YB moves in the, I'm sorry, that is positive, but then it's minus 1/2 A T squared. There we go. Okay. So now I have the x as a function of time, and I've got the velocity as a function of time, and I can eliminate the time and solve for the position as a function of velocity, right? Which you could do, and that's in effect what we did earlier here. That's what we did here. What we got was the velocity as a function of x here. And so what's contained, we've got more information in this solution. We've got the time, not just the velocity as a function of displacement. We've got the time. So we've got a more complete solution this way. But do you see how those two things relate to each other? One is more work in the sense of more algebra, setting up the equations and solving them. The work-energy theorem, in a sense, short circuits that if all you're looking for is the velocity, if you're not looking for something else. If you wanted the tension, there's no way the work-energy theorem is going to help you. You can't find the tension in the rope through the work-energy theorem. So if I asked you for the tension, you'd have to do something, I think, like this. Use Newton's equations, solve for the tension. Okay? Does that help? It's a rich problem. There's a lot here. You can do it these two different ways, depending on what you're looking for. And I highly recommend, in fact, that's one of the problems you're going to do on Friday. You're going to do it two different ways. You're going to do it with the forces and accelerations and solve for the motion and time. You're also going to solve using the work-energy theorem. Find the velocity as a function of displacement using the work-energy theorem. Okay, that's one thing to keep in mind. The other thing to keep in mind is I did this problem, and it's got both conservative and non-conservative forces. I used the work-energy theorem for all forces. It applies regardless of whether it's conservative or non-conservative. So you can either calculate the work done by all forces, or you can separate out the conservative forces and use the work-energy theorem in a different form, which is in terms of the kinetic and potential energies here, as in the bottom there. Okay, any questions about that? There's a lot there. It's a lot of meat. It's a good problem to study. Okay, the next problem, is that the one where the barrel falls off the waterfall? Okay, so returning to the work-energy theorem, we could write it this way, or we could write it this way, where this is the work done by non-conservative forces. So these are non-conservative or dissipative. And in this problem, are there any non-conservative forces? No. You've been told to neglect air resistance and those sorts of things. So in this case, then we're saying that the total energy is conserved. The lack of dissipation means the total energy is conserved. And so I can say then that the increase in kinetic energy comes at the expense of potential energy. And so because it starts off at rest, the increase in kinetic energy is all of the kinetic energy at the end, and the loss of potential energy is negative mgh, and so the negative of that is this, and so then that gives me the velocity is the square root of 2gh. Again, do a quick dimensional analysis. What is dimensionality of g? Mr. Flanagan, what's the dimensionality of g?
Length per time squared.
And h?
Length.
Square root of that gives length per time. Is that good?
Yes.
That's we wanted it to have velocity. And you can try a couple of other things. If the waterfall is higher, if it has farther to fall, will it have more velocity at the bottom? Yeah. So that's borne out by that relation. If the acceleration due to gravity were bigger, if we did this on Jupiter instead of the Earth, if we could manage to find a waterfall on Jupiter anyway, if you did that, then g would be bigger and you expect to have more velocity at the bottom. Okay? Same thing in this one, only it's in the next one, number 32, except it doesn't go up as high. It goes part way back up. So we have, I think, is this what it was? It starts off h here, rolls down. Is that what the situation was? Okay. So does it matter the shape of the hill?
No.
As long as it gets to the same endpoints. Remember, the work done by gravity doesn't depend on the path. As long as there's no friction. If there were friction, it would matter, the shape of the hill, because it's going to do more work on the bottom trajectory because it's got farther to go if there were kinetic friction. So it'd have less speed if it takes a longer path. It's going to have less final speed. But if there's no friction, then the velocity at the end doesn't matter, right? As long as it isn't prohibited. This would be a problem if it started off with no kinetic energy, because it's not getting over that hill at all. It's never going to get there. Okay. All right, number 66. What you need to remember in general, that the force points in the direction of decreasing potential energy. So if I have something like potential energy due to gravity, the potential energy increases as I lift the body. As the body goes up, the work done by gravity is increasing, so its potential energy because of gravity is increasing, and the force is pointing in the direction of decreasing potential energy. And so you have this relationship that the force is, well, I suppose generally speaking, writing it in terms of some kind of displacement x, it's the negative derivative of the potential energy with respect to x. So in the case of gravity, this is the potential energy due to gravity. Force due to gravity is going to be minus mg, right? It's the derivative of the potential with respect to whatever variable is changing. Yes, sir?
Why do we use V for potential energy?
I don't know.
Just confused.
That's a good question. Sounds like a historical question, you know.
Like coefficient.
Somebody's name started with a V.
Isn't there was something in the book about it. It was something like they thought that
Oh, it's in the book? Oh, I'll have to look for it there. I read the book more than once. I don't remember that. If you could find the page, I'd like to.
Can we use something else?
How about K for kinetic energy? Oh, kinetic maybe.
I always use U.
U is fine. I don't care. As long as you.
I get it mixed up with velocity.
You know.
I don't.
Just say it's potential energy, whatever.
But V is so much cooler and so demanding. Like V.
If you're concerned about getting it mixed up with velocity, you could put some put some things on top
It's
there.
gonna make a lot more drag than you like let it go on free fall. It's just gonna be slowing it down.
Okay. All right. So in the case of the potential energy here, he gives the potential energy is dependent on is it over r squared? Is that right?
Yeah, over r squared.
That's an odd one.
You have to put it in terms of R or X.
Yeah, sure. Just think of it. You're just moving it, right? So what is changing r?
Oh.
So the derivative of v with respect to r, in other words, v prime of r is what? Mr. Avery, what's the derivative of v of r with respect to r?
It's negative 2ar to the negative third.
Correct. Okay. So if a is positive, let's suppose a is positive to make it definite here. This potential energy looks like this, right? It's dropping off as a function of r. So the force points in the direction of decreasing potential energy. And so the force is going to be pushing it towards increasing r. If r is the distance between the two bodies, it's a repulsive force that's associated with this. So F is minus dv dr, so it's 2a over r cubed. So if a is positive, the force is positive, it's pushing it away. And notice that 1 over r cubed, so it gets weak pretty fast. If you double the distance, the force gets 1/8 as intense as it was before. Force due to gravity has a potential energy. If we get far away from the planet, far away from the Earth, it goes like 1 over r. We'll find when we do in chapter 8. In which case the force due to gravity is attractive and goes like 1 over r squared. Like that. Take the derivative with respect to r. The other one that you have in the problem is just it's proportional to distance, and so the force is in the opposite direction and is constant force. In the next chapter, we'll deal with a force which is not constant. We've dealt with, up to this point, forces that are either they're no forces or they're forces that are constant, that is, don't change, either because of position or because of time. Now we're going to start dealing with, in chapter 6, forces that change with position. If I move the body, the forces acting on it are going to change. And that's when we're going to have to be now developing more mathematical procedures for dealing with variable forces. Okay, the last problem that I want to work on here then today, well, let's see, the last problem in the homework, has to do with this question of the general binary collision in one dimension. So I've written up here the solution, which is a little bit more general than what you were assigned.
Wait, so what you were saying before, does that mean it'll no longer be uniform linear acceleration?
Correct. We're going beyond uniform acceleration as of chapter 6. Okay, so this is the general situation, and I think you were given that the target, the second mass was at rest, and you were to solve it. But I'm going to give you the general solution. Doesn't matter, as long as they collide. So in other words, V1 has to be bigger than V2 in this. So before, and now let's do the inelastic collision. The inelastic collision is easy because they stick together, and therefore we have the combined masses moving with the same speed, v prime. So in other words, the inelastic collision says they're connected, so they have the same speed after the collision. So how do we solve for v prime?
First, do conservation of momentum.
Correct. Conservation of momentum. All binary collisions conserve momentum. Not all binary collisions conserve kinetic energy, but all binary collisions conserve momentum. So the momentum before is going to be m1 v1 and then plus m2 v2. The momentum afterwards is going to be m1 plus m2 moving and v prime, right? And so equating the momenta gives me this. So that's it. The inelastic collision is really easy in one dimension. It's actually easy in 3 dimensions. It's the same thing in 3 dimensions.
Why are the lines under P? Is that something special or it's just?
Pardon?
Like, do you put the line under your P to indicate like
Total. I want a capital P here. Yeah.
Oh, okay. Okay, that makes sense. And if it was in between, that would be like the lowercase.
Yeah, lowercase would be the momentum of the individual bodies. That's just me, though. But I'm just trying to denote total momentum of the system as opposed to the momenta of the parts.
Yeah, that's what's up. I see how you popping it. It's cool.
Now, does this resemble anything? Do you recognize this, by the way?
The geometric thing, or not geometric, the algebraic
Yeah.
equation you put on the thing.
Yeah.
Center
Keep
of
going.
No, I like that.
Yeah. Mr. Averett?
I don't know.
Mr. Vestal.
The center of momentum.
Center of mass.
Center
Center of mass. It's the velocity of the center.
Center of mass, that's it.
Right. It's the velocity of the center of mass, v prime. Which makes sense because where is the center of mass after the collision there? If you were to locate it, it's someplace between those two masses and it's moving with them. And so the motion of the composite body, it's going to be at the velocity of the center of mass. So this is the center of mass velocity. And it happens that after the collision there really is something there. Before the collision, there's nothing at the center of mass. Well, I say there's nothing. Neither body is at the center of mass. To be more precise. Okay, let's see. Okay. All right, so let's do the same thing then now for the elastic collision in one dimension. And this gets tricky. It's a little harder. And it's straightforward algebra, but if you make any mistakes along the way, then you get a mess at the end. It's not so bad if you don't make any mistakes. So we have the same diagram, so I'm not going to draw. Oh, no, it's not the same diagram. The after, of course, is different. After. V1 prime into V2 prime. Okay, so I still have conservation of total momentum. What else is conserved in an elastic collision by definition?
Energy. Kinetic energy.
Yes, kinetic energy specifically, not total energy. Kinetic energy does not change during across a binary collision. So now I want to write the two equations to represent this. M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. And kinetic energy here, now there's a factor of a half all the way through this. I'm going to drop the half, all right? Because everybody in this equation has a half. I'm going to drop all the halves because I want to simplify things. Okay, now, before you get started, identify what's unknown. How many unknowns are there, and what are the unknowns? Mr. Sharp, what are the unknowns in this?
I'm not sure. And
so we set up the collision. Certainly, the two masses are specified, and the initial velocities are specified. So M1 and M2, as well as V1 and V2, are both specified. So what's left over?
V prime 1, V prime 2?
Yes, sir. Those are the two unknowns. So what we have on the right-hand side, we have terms that involve the unknowns. This one and this is the same. This one is the same. So we have two unknowns, two equations. But this one's a little different than ones we've dealt with before. In what way is this different? Mr. Kelly, can you see?
They're both they're not head-on. They're both.
So I'm asking a strictly mathematical question here. In terms of the equations, what's different about these equations than one we did, say, earlier today when we had three unknowns, we had three equations, three unknowns, and we solved it? This one is, yeah, Mr. Flanagan.
When they move a point, they could be at different speeds.
No, I'm looking for a strictly mathematical thing. Just the mathematical form of the equation is what I'm going after here. Does anybody see it? The second one's quadratic. Which makes it a level of difficulty harder, because if they were two linear equations, it would be really easy to solve. One of them is quadratic, which means you could potentially have two solutions coming out of this. Possibly. Okay, if we look at this in terms of the two unknowns that we want, v1 prime and v2 prime, those are the things we want to know. And the first equation there says that the momentum after the collision is equal to the momentum before. So what we have is a linear relation between v1 prime and v2 prime. m1 v1 prime plus m2 v2 prime is equal to some constant, which is the total momentum beforehand. So that looks like an equation. A linear equation will look like that, a straight line. The delta p equals 0. The momentum conservation means that the two velocities, final velocities, must fall on that line. Now how about the second one? What does the second equation look like? Anybody know? Anybody? It's not a circle. If the masses were the same, it would be a circle. It's not a circle. It's an ellipse. So I have some ellipse here, like this. How many? So so this is the delta k equals 0, and the delta p equals 0. If the two equations line up the way I have drawn them here, we would have two solutions, wouldn't we? We'd have one here and one here. It's possible. It's possible also that the straight line falls outside of the ellipse. We have no solutions. Or it might be that just kiss it, so there's one solution twice.
Oh my God.
We're not out of high school yet. All right, so let's look at the... okay, so now the way to solve these two equations, and I gave a hint in the homework, and I'm not sure, I wonder how many people picked up on this. I said group the terms according to mass. So you see here, where does m1 occur? Well, I've got m1 here and m1 here. I've got them on both sides of the equation. I want to put them on the same side. I want to put all the terms involving m2 on the other side, and do the same thing for this equation. And that's what's shown in the solution. And if you do that, you get m1 v1 minus v1 prime equals m2 v2 prime minus v2. That's the delta p equals 0, but rearranged so that the mass terms involving m1 are together, terms involving m2 are together.
How come you don't put the v1 prime minus v1?
Let's see, because if you
It just works out that way.
Yeah, if you subtract m1 v1 prime from both sides, it becomes negative m1 v1 prime on the left-hand side. And then we have to move the m2 v2 over to the right-hand side, so we subtract it from both sides. Okay, so we rewrite our two equations collecting the terms by mass. So if you see that part, then the rest of it is easy. If you didn't see that part, then it's a mess, right? Yeah. It's straightforward algebra. If you do your algebra right, you solve the quadratic equation, you'll have two roots. Pretty messy, okay? There's still two roots here. Still two solutions that are possible. But I'm going to do something here. I've got two equations. I'm going to call them A and B. What if I divided B by A?